A black hole is a region in spacetime with gravity so strong that nothing, not even light, can escape. The event horizon is the point of no return, the boundary around a black hole. Think of it like a waterfall. Once you're over the edge, there's no going back. Around a black hole, there's an innermost stable circular orbit. Beyond this point, matter inevitably falls toward the event horizon. As matter approaches a black hole, it forms an accretion disk that warps with the distorted spacetime. Eventually, some of this matter crosses the event horizon and can never escape. The event horizon acts like a one-way membrane surrounding a black hole. Matter and radiation can enter, but nothing can exit once it crosses this boundary. It's not a physical barrier you'd bump into. Rather, it's a region of spacetime so warped that escape is impossible. Let's look at the structure of a black hole. The event horizon is this boundary, acting as a cosmic point of no return. Let's see what happens when particles approach a black hole. Once they cross the event horizon, they can never escape. Here we see a tidal disruption event, where a star is torn apart as it approaches a black hole's event horizon. The material crosses the boundary and becomes trapped forever. To summarize, the event horizon is a cosmic point of no return. It's a one-way membrane for matter and energy, not a physical surface, but a boundary in spacetime, and crossing it means never returning. What happens when you cross the event horizon of a black hole? According to classical general relativity, once you cross the event horizon, you're destined to be pulled towards the singularity at the center of the black hole. As you approach and cross the event horizon, tidal forces become extreme. These forces are caused by differences in gravitational pull across an object. This results in a process often called spaghettification, where you would be stretched vertically and compressed horizontally. These extreme tidal forces are a result of the severe warping of spacetime near the black hole. Once inside the event horizon, all possible paths in spacetime lead to the singularity. There is no trajectory, however powerful your engines, that can avoid the center. At the very center of a black hole, general relativity predicts the existence of a singularity, a point where our current understanding of physics breaks down. According to Einstein's theory, as matter collapses into a black hole, it forms a singularity where spacetime curvature becomes infinite and matter is crushed to infinite density. However, this prediction reveals a limitation of general relativity itself. The theory breaks down at quantum scales, predicting physically impossible scenarios like infinite density. This suggests that general relativity cannot fully describe what happens at the singularity. Many physicists believe that quantum mechanics offers alternative explanations. Quantum gravity theories suggest that quantum effects may prevent the formation of a true singularity. Instead, matter might reach a finite maximum density, or spacetime itself might have a fundamental granular structure at the smallest scales. Beyond the basic quantum framework, researchers have proposed more exotic possibilities. Some suggest a bounce, where matter compresses to a point before expanding into a new universe. Others propose a fuzzball of quantum strings, or a Planck star with a core of quantum spacetime. While we can mathematically define the singularity and visualize its effects, its true nature remains one of the greatest mysteries in physics, a place where our current theories of spacetime simply cannot go. The singularity represents the boundary of our current understanding, a place where general relativity and quantum mechanics must somehow unite into a more comprehensive theory. In recent years, astronomers made a breakthrough in black hole research by capturing the first ever images of these cosmic giants. This was accomplished using the Event Horizon Telescope, a global network of radio telescopes working together as a virtual Earth-sized telescope. The EHT connects telescopes from across the globe, from Antarctica to Spain, creating an Earth-sized virtual telescope with unprecedented resolution. In 2019, the Event Horizon Telescope revealed the first ever image of a black hole, known as M87 star, located at the center of galaxy M87. This orange ring shows hot gas circling the black hole's event horizon, with the dark central region representing the black hole's shadow. Subsequent observations of M87 star in different years confirmed the stability of this enormous black hole, which is 6.5 billion times the mass of our Sun. In 2022, the EHT team revealed an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This region had been studied for decades using other wavelengths, but directly imaging the black hole itself was a tremendous scientific achievement. Despite appearing similar in images, these two black holes differ dramatically in size. M87 star is enormous, while Sagittarius A star is much smaller, though still about 4 million times the mass of our Sun. These groundbreaking images confirm Einstein's predictions about black holes and provide direct evidence of their event horizons. The bright ring we see is not the event horizon itself, but hot gas orbiting just outside it, with the dark central region being the black hole's shadow. These images represent one of the greatest achievements in modern astronomy, revolutionizing our understanding of black holes. The Event Horizon Telescope collaboration is pushing the boundaries of black hole observation. This global network of radio telescopes works together as a virtual Earth-sized telescope to study black holes in unprecedented detail. The next frontier in black hole research is creating movies rather than static images. These movies will reveal dynamic processes including gas orbiting the black hole, magnetic field fluctuations, accretion disk dynamics, and jet formation. The Black Holistic Project is an EU-funded initiative running until 2029. This ambitious project uses supercomputing and advanced simulations, while also building a new radio telescope in Namibia called the Africa Millimeter Telescope. The scientific goals of these projects are ambitious and groundbreaking. Researchers aim to create the first videos of swirling plasma around supermassive black holes, increase image resolution by 50%, study jet formation, and test Einstein's theories in extreme conditions. Creating movies of black holes requires significant technical advancements. These include global coordination of radio telescopes, processing petabytes of synchronized data, advanced computational modeling, and new algorithms for dynamic visualization.
When black holes are viewed through the lens of quantum mechanics, new questions emerge that challenge our classical understanding. Stephen Hawking theorized that quantum effects near the event horizon cause black holes to emit radiation. Virtual particle pairs can be separated, with one particle falling in and the other escaping as Hawking radiation. At the center of a black hole, general relativity predicts a singularity with infinite density and zero volume. Physically, such infinities shouldn't exist, pointing to limitations in our current theories. Theories like Einstein-Lovelock gravity attempt to resolve these inconsistencies by incorporating higher-order corrections to Einstein's field equations. Some scientists, including Stephen Hawking in his later years, questioned whether true event horizons exist. They proposed apparent horizons instead, temporary boundaries that can change over time. With apparent horizons, information could potentially escape a black hole after a long time, preserving quantum information and avoiding the information paradox. Quantum gravity seeks to unify quantum mechanics and general relativity, our two most successful but incompatible theories of physics. Leading approaches include string theory, which replaces point particles with tiny vibrating strings, and loop quantum gravity, which quantizes spacetime itself into discrete units. A fascinating recent development suggests that wormholes, theoretical tunnels through spacetime, may be mathematically equivalent to quantum entanglement. This connection, known as the ER equals EPR conjecture, proposes that entangled particles may be connected through tiny wormholes in spacetime. If correct, this would mean that the interior of a black hole could be connected to other parts of the universe through quantum mechanical pathways. The black hole information paradox remains one of physics' greatest unsolved problems. Quantum mechanics requires information to be preserved, but black holes seem to destroy information. Proposed solutions include the holographic principle, which suggests information is encoded on the black hole's boundary, black hole firewalls, which propose a barrier of energy at the event horizon, and black hole complementarity, which suggests different but equivalent descriptions for observers inside and outside the black hole. Quantum effects at the event horizon represent the frontier of theoretical physics. The reconciliation of quantum mechanics and gravity will likely transform our understanding of black holes and perhaps the nature of space-time itself. As our understanding of quantum gravity advances, we may finally resolve the mysteries that lurk at the boundaries of black holes.
Despite our remarkable progress in understanding black holes, many fundamental mysteries remain unsolved. Several key questions continue to puzzle physicists and astronomers. We still don't fully understand the true nature of the singularity at a black hole's center. The interaction between quantum mechanics and gravity near black holes remains one of physics' greatest unsolved problems. The information paradox, whether information that falls into a black hole is truly lost, continues to challenge our understanding of fundamental physics. And we still can't fully explain how supermassive black holes managed to form so quickly in the early universe. The singularity presents perhaps the greatest mystery. General relativity predicts a point of infinite density and space-time curvature, but quantum mechanics suggests such infinities cannot exist in nature. Another major puzzle is how supermassive black holes reached billions of solar masses when the universe was less than 1 billion years old. Current models of black hole growth can't easily explain this rapid development. Quantum effects near black holes blur the line between scientific fact and theoretical fiction. Stephen Hawking predicted that black holes emit radiation and eventually evaporate, but this radiation remains undetected. The information paradox remains one of theoretical physics' greatest unresolved debates. What happens to information that falls into a black hole? Various quantum gravity theories, including string theory and loop quantum gravity, offer different solutions, but conclusive evidence remains elusive. The future of black hole research is incredibly promising. Enhanced versions of the Event Horizon Telescope will capture higher resolution images of black holes. Next-generation gravitational wave detectors will observe more black hole mergers with unprecedented precision. Scientists are working to create the first movies of black holes, showing the dynamic processes occurring around their event horizons. Theoretical and experimental advances may finally help us understand quantum effects near black holes. Black holes remain among the most fascinating and mysterious objects in our universe. Each answer we find leads to new questions, continuing the endless journey of scientific discovery.